Hello everyone. In this lecture we will continue studying public key cryptography by studying crypto algorithms that use elliptic-curve cryptography or ECC. ECC-based encryption and digital signature schemes can be used as an alternative to the RSA crypto system, and recently ECC has become increasingly popular as it provides better efficiency when compared to RSA. But before we get into it, let's look at Diffie-Hellman key exchange, which is another public key crypto algorithm you should know and which will help you a lot to understand the idea behind elliptic curve cryptography. Diffie-Hellman key exchange was the first public key crypto algorithm which was invented by these three gentlemen only a year before RSA. So Diffie is the last name of the inventor Whitfield Diffie, and Hellman from Martin Hellman. For some reason, Ralph Merkle's last name did not get into the title, but by the way, this Ralph Merkle is the guy behind hash tree or Merkle tree, which we studied in the lecture about hash functions. Anyhow, so this is the first public key cryptography algorithm, and as its name implies, the purpose of the algorithm is to exchange a secret key over a public channel. Let's take a look at it. The idea behind this key exchange algorithm is pretty simple, and here's an example. Let's assume that there are two parties who want to agree on a secret key over a public channel, which is being eavesdropped by an attacker. The requirement is that both parties agree on some common number, 2 in this case. This number must not be secret, so the attacker knows that the common number is 2. Then each party has to generate a random secret number. Now this number has to be kept secret. It stays only with that party. What do they do next? They take the common number and take it to the power of the random number they have. They do it on both sides, as you see, and then they exchange the result of the exponentiation over the public channel. Then they take the value received from the other party and take it to the power of the random secret number. Surprise, surprise, it turns out that as the result they get the same number. And this is because of the properties of exponentiation. It does not matter if we take 2 to the power of 5 and then 4, or vice versa. The result is the same, right? Right. Very good. So now both parties have this common shared secret, which they can use as a secret key to establish a secure channel. Now, the security claim here is that only these two parties know this number. An attacker cannot calculate it unless the attacker knows the private exponent of one of the parties. The attacker knows the common number 2 and knows that this number 32 is the result of taking the common number to some unknown power, but the attacker cannot recover the private exponent 5 from this number 32. So you can think of this random number as a private key and this result of the exponentiation as a public key, as it is not possible to derive the private key from this public key. Well, this is actually not true. If you're a bit familiar with math, you know that solving a logarithm is not that hard of a problem. Even if these numbers were very large, your calculator could easily solve the logarithm. Maybe even you could do it on a paper. So to achieve security, in practice, the multiplicative group of integers modulo prime p is used here. And in such a case, we call it the discrete logarithm problem. And it is defined as follows. It is hard to find x given that 2 to the power of that x is 32 modulo prime p. So if we remove mod p, it is a simple logarithm which is easy to solve. If we add mod p, we get a discrete logarithm which is a very hard mathematical problem to solve. If you can figure out how to efficiently solve it, you can become famous and rich overnight. Sure, you can brute force trying out different x values here until the result is 32, but that's the best we can do. This discrete logarithm problem provides not only this Diffie-Hellman key exchange algorithm, but is also used to implement the ELGAMAL encryption scheme and the DSA digital signature algorithm. And then there are also other less popular crypto schemes based on the discrete logarithm problem. It is very important to stress here that this algorithm is secure only against passive eavesdropping, namely where the attacker is able to only listen but not interfere with the data exchanged. If the attacker is also able to modify the data, the attacker can replace this value 32 with a value that is generated using a random number picked by the attacker and not by the legitimate party. Efficiently, the attacker will be able to spoof or impersonate this other party, and we will end up establishing a secure key not with the legitimate party but with the attacker. Therefore, it is very important to authenticate this value we receive from the other party. The same as for RSA, we have to verify the public key belongs to the party we want to communicate with. Now, the idea behind elliptic-curve cryptography is that instead of using the multiplicative group of integers modulo p, we can use the multiplicative group of points defined on an elliptic curve. Here is how it works. In cryptography, elliptic curve is a math construction that is defined by an equation like this. The shape of the curve will depend on these coefficients a and b and this prime p here. You can invent your own curve simply by picking these coefficients, but in practice we are using standardized curves with specific security properties. Anyhow, once you have this equation, you can draw the curve geometrically. Looks something like this. Here we see a continuous line, but there are actually a finite number of points on this curve defined by integers x and y here. Now, let's say we have some point p here. What we can do is that we can perform point addition. We can add a point to itself. To do it geometrically, we draw a line that only touches the point p, like this. Then we draw a vertical line perpendicular to the x-axis and where it crosses the curve. This point here would be p added to itself. And we can continue adding p to itself again and again and again, jumping all over the curve. We don't have to do it geometrically, as there are simple formulas for point addition and doubling. So we can do it by using simple integer arithmetics on integers x and y. Now, remember the discrete logarithm problem where it was hard to find x given the result of a exponentiated to x mod p. Here we have something very similar. The elliptic curve discrete logarithm problem is defined as follows. I give you some point t here, and you have to tell me how many times this point p was added to itself to this point t, to get to this point t. And this is actually a very hard problem. Yes, we can brute force by adding p to itself until we reach t, but this is infeasible if the curve is big enough. Okay? And that's it. That is the entire idea behind elliptic curve cryptography. All the schemes which are based on the discrete logarithm problem, we can directly convert to the elliptic curve discrete logarithm problem just by using point multiplication instead of modular exponentiation. We can have elliptic curve Diffie-Hellman, elliptic curve ELGAMAL, elliptic curve digital signature algorithm, and so on. The idea is exactly the same. In fact, in practice, you will most likely not encounter a plain Diffie-Hellman or a plain digital signature algorithm, but instead the elliptic curve version of it. So why is the elliptic curve version preferred? Because compared to the standard discrete logarithm and RSA, elliptic curve allows the use of smaller key sizes that provide the same security level. The key sizes are smaller, the ciphertext is smaller, and the crypto operations are faster. For instance, a 256-bit ECC has the same security level of 3072-bit RSA. which is believed to provide 128-bit security level. 256 bits here is the size of the field defined by prime p here. So for elliptic curves, the provided security level is half of the size of the curve. A 256-bit curve provides a 128-bit security level, a 160-bit curve only 80 bits, and so on. Some years ago, elliptic-curve cryptography was pushed as a successor to RSA. But since elliptic-curve cryptography will be broken the day powerful quantum computers are built, it does not make much sense to spend resources switching from RSA to ECC. It is better to wait a bit and upgrade to some public key algorithm which will be quantum computer safe. But we don't have any good algorithms standardized yet. Note that because of the shorter key size, ECC is weaker than RSA against quantum computers. So we can expect that first a quantum computer will be built that will break 256-bit ECC, and only then one that can break 3072-bit RSA. Now, here is an incomplete list of standardized or so-called named curves. These are the names of the most popular curves you will see. Some of the curves have been standardized by several standardization institutions, and therefore they have several names. The number in the name usually specifies the bit size of the curve. While there are several standard curves with the same size, they have slightly different properties. For example, this 256-bit curve SITSP256K1, which is used in Bitcoin, has a special structure, and therefore an optimized implementation can provide up to 30% speed up compared to this NIST 256-bit curve. This NIST 256-bit curve is likely the most popular curve. As you see, it has 3 names assigned by different standardization institutions. This 256-bit curve is used in the Estonian mobile ID, and this 384-bit curve is used in the Estonian ID cards. These 2 curves are special purpose curves invented by Daniel Bernstein. This one is optimized for Elliptic-curve Diffie-Hellmann, and this one for digital signatures. Let's discuss a bit more about the so-called elliptic curve domain parameters. Here is the illustration of the equation. So P here defines the size of the field. We will look only at the curves where this is a prime number. There are elliptic curves over binary fields, but they are not used much in practice. So the P here limits the length of a point's x and y coordinates. For a 256-bit curve, P will be 256 bits long, meaning that the x and y coordinates will each require 32 bytes. A and B are equation parameters or coefficients in this formula. They can have different values. G is a generator or base point on the curve. This is a constant elliptic curve point that parties can use as a pre-agreed common number in the Diffie-Hellman protocol. So the starting point P that can be multiplied with a party's private key value to obtain or generate the resulting point T, or the public key. So basically, this is a safe base point that parties can use right away without having to agree on it separately or explicitly. Otherwise, there is nothing special about this point. Other points on the curve could have been used as well. N is the order of the curve, or the total number of points on the defined curve. The elliptic curve forms a so-called cyclic group, meaning that if we keep adding a point to itself, then eventually we will return to the initial point. So this will happen after we add a point to itself n times or multiply a point by n plus 1. H is a cofactor. It specifies the number of cyclic subgroups that are on the curve. For NIST curves, the cofactor is 1, which means that there is a single big cyclic subgroup that has n number of elements or points in the group. If the cofactor is 1, then the order n will be a prime number the same bit length as p, but just a bit smaller than p. Meaning that for a 256-bit curve, there usually exists slightly less than 2 to the 256 different points, and hence the number of possible private keys. Another useful property of having a cofactor of 1 is that any other point on the curve can be safely used as a generator to generate all other points. If you're interested, you can dump curve parameters using OpenSSL ECParam specifying the name of the curve. Here we see the prime p, coefficients a and b, generator g, its x and y coordinates, order of the curve denoted by n, and the cofactor 1. Let's look closer at the elliptic curve point operations. The first operation is point addition. We can add together two distinct points to get some third resulting point. This is the formula for calculating point addition. Not important to know, just for you to see that there is no rocket science. We just plug x and y values of both points into the formula and get back the x and y values of the resulting point. Then there is point doubling. When we want to add a point to itself, we cannot add a point to itself using the point addition formula. We have to use a slightly different formula where lambda has to be calculated using the equation you see here. Then there is point multiplication, where we can multiply a point with some integer, sometimes called a scalar. To denote point multiplication with scalar, we use this times sign. And to distinguish point and scalar, we use a lowercase letter for the scalar and uppercase letter for the point. So how do we multiply the point? The naive approach would be to add the point to itself k number of times, but that would be very slow. We can use the square and multiply algorithm, which we used for exponentiation, but in this context, we call it double and add. So there is no special equation for point multiplication. What we do is that we double the point as much as we can and then add missing intermediate doubled points to get the result. Then there is a special point called point at infinity, which is like 0. We cannot do anything useful with it. We will get to the point at infinity if we multiply a point n times, where n is the order of the curve. So this is simply a special case that needs to be handled. Point negation is finding a point such that adding it to itself will result in point at infinity. This is useful if for some reason we want to subtract a point from another. We can negate a point easily by changing the value of the x, y value by setting to be the prime p minus the y value. Then we have point validation, which is simply checking whether the point is on the curve. To verify it, we simply put x and y of the given point into the elliptic curve equation, and if the equation is satisfied, then the point is on the curve. Okay? Okay, very good. Let's look at the elliptic curve version of the Diffie-Hellman key exchange algorithm. So we have Alice and Bob who want to agree on a common shared secret. Here we assume that both Alice and Bob have pre-agreed which elliptic curve to use. So first, they both generate a key. The generation of the private key is trivial. We just have to generate a random integer from 1 to n minus 1, where n is the order of the curve. The public key is a point on the elliptic curve calculated by multiplying the generator point g with the private key integer g. If a larger value than n is used as a private key, then at point multiplication it will simply be reduced modulo n, because the size of the curve is n and the group is cyclic. Then the parties exchange their public keys, sending them over the channel that is potentially eavesdropped by an attacker. And then they validate each other's public key to verify that it is indeed a valid point residing on the elliptic curve. Shared secret calculation is performed by multiplying the public key received from the other party with their private key value, and as a result, both Alice and Bob will obtain the same point QAB, which is the result of multiplying generator G with DA and DB. So the order in which multiplication is performed does not matter here. The scheme is secure because the attacker cannot recover the private key from this public key. Remember, it is very hard to figure out how many times the point G was added to itself to obtain this point Q here. Now, why it is important to validate the public key here? The reason is that if point validation is not done, then the other party can send us a specially crafted value that, when multiplied with our private key, will produce a result that may leak information about our private key. Let's consider a case where we receive a point that is on some other curve, which has a very small size. Let's say the curve has an order of 2, meaning that there are only 2 points on that curve. So when we multiply that point with our private key here, the possible result here will be one of the 2 points that are on the curve, depending on which our private key, but depending whether our private key is odd or even number. So by learning which point we obtained here, the other party will deduce the last significant bit of our private key. The other party can then repeat the attack using different sized curves, recovering our private key bit by bit, which is not good. So to stay on the safe side, validate points received from untrusted parties before performing calculations with them. All right, so now we have a common shared secret point QAB here. To obtain a byte string that we can use as a shared secret, we take the x coordinate of this point QAB and encode it to a byte string. So for a 256-bit curve, we will get a 32-byte shared secret here. And it is okay to throw away the value of the y coordinate, because for each x value on the curve, there exist only 2 y values. So the y value provides just 1 additional bit of entropy here. Then once we have a shared secret, we can use it to encrypt data using symmetric encryption schemes. So this is the standard way of how to encrypt data using elliptic-curve cryptography. We use hybrid encryption, where elliptic-curve Diffie-Hellman is used to derive a symmetric transport key. In RSA, we could encrypt the plaintext directly, but in elliptic-curve cryptography, this is not practiced, as here we would have to represent our plaintext as a point on the curve, which is possible, but also problematic. So we use this approach instead. It is important to highlight that using this elliptic-curve Diffie-Hellman based encryption scheme, anyone can encrypt data for Bob, even if they don't have a permanent key pair whose public key is trusted. For example, we can take Bob's public key, generate a so-called ephemeral or one-time key pair, calculate a shared secret, encrypt data using the shared secret, and send it together with our ephemeral public key to Bob. Bob can then derive the shared secret using his private key and decrypt the data. So in the case of RSA, we could simply take the public key of the other party and use it to encrypt data, but here we have to generate some temporary throwaway key pair in order to do that. Okay? Let's look at the elliptic-curve private key file format. We can generate the private key using the OpenSSL tool, passing the genPK parameter specifying the algorithm elliptic curve, the name of the curve we want to use, and where to write the private key. This is the private key in PEM format. we can convert it to their format, and if we dump ASN1 it, we can see this ASN1 structure, which is defined in this RFC. So what do we see here? There are two object identifiers. The algorithm object identifier here specifies EC public key, and the parameters specify the object identifier of the named curve. Alternatively, this parameter field, in this parameter field, we can encode all the domain parameters of the curve. But since we are using a standardized named curve here, we can simply specify the object identifier of the curve. The EC private key structure is encapsulated as an octet string. This is the version number of the private key file format. This is the 32-byte private key encoded as octet string. Optionally, it can also contain the public key encoded as a bit string. The first byte with value 4 is a constant, then follows the 32-byte x coordinate and 32-byte y coordinate of the public key point. The public key file format. We can use this command to generate the public key from the private key. As you should recall, the public key is generated by multiplying the generator point g with the private key integer d. This is how the public key looks in PEM format. If we convert it to their format and dump ASN on it, we will see the subject public key infrastructure defined in this RFC. The algorithm object identifier here specifies EC public key, and parameters specify the object identifier of the named curve, or alternatively encode all the domain parameters of the curve. The public key here is encoded as a bit string, encoding the points x and y coordinates here. A note about elliptic curve point compression. So it is possible to encode an elliptic curve point in a more compact form than you saw on the previous slide. We can use this command to convert our uncompressed public key representation to a compressed format. If we dump ASN1 the result, we can see that this bit string is now 32 bytes shorter. The idea behind point compression is as follows. As I mentioned before, for every x value on the curve, there are only two possible y coordinates that the point can have. So instead of storing the full value of the y coordinate, we can just use a single bit to specify which of the two possible y values is the y value of the point. And we store this bit in the first byte of the encoded elliptic curve point. So the first byte of the elliptic curve point value indicates whether the point compression is used. Value 4 indicates that the uncompressed form is used, meaning that the encoding of full x and y coordinates follow. Value 3 indicates that the compressed form is used and that the value y is odd. And value 2 indicates that the compressed form is used and the value y is even. Now, for the public key you see here, this byte has value 3, indicating that the odd y from the two possible y values is the y value of the point. To decompress the point, we would plug in the x value in the equation of the curve, find both y values, and pick the y value that is odd. Okay? Then a byte with value 0 is used to indicate the point at infinity. So if the first byte is a 0 byte, then no x and y values follow. The point at infinity, of course, is not a valid value for a public key, but this is how we would encode it if needed. To summarize, by using this point compression method, we need half less space to store a point. However, in practice, you will not see this point compression method being widely used, because until recently it was covered by a patent that expired only in 2018. The last topic for this lecture is the elliptic curve digital signature algorithm, which you will have to implement in the homework. The elliptic curve digital signature algorithm, or ECDSA in short, is the elliptic curve version of the DSA algorithm. Other signature algorithms exist also, but this is the only one widely used in practice to create signatures using elliptic curve keys. So here is how it works. To sign some data, we need a hash value h of the data and an elliptic curve private key denoted by d. First, we start by generating a random nonce k in the range from 1 to n minus 1. The n here is the order of the curve. Then we calculate the random point r by multiplying the generator with the random nonce key and set the value r to its x-coordinate. So the lowercase r is the x-coordinate of this point r. Then we calculate the modular inverse of the nonce k such that the result of k multiplied by k inverse modulo n is 1. The inverse can be easily found using the extended Euclidean algorithm. Then we calculate the value s by using this formula. Inverse of nonce k is multiplied by hash added to the random r value and is multiplied by private key d, everything modulo n. And that's it. We have created an ECDSA signature of this hash h here. Now, what is the complexity of this signing operation? Note that this multiplication of the base point g with the random nonce key is the only elliptic curve point operation here. This calculation of s here is pure integer arithmetic without involving any elliptic curve operations. And this is the reason why ECDSA signing can be implemented very efficiently. The resulting signature consists of two values, r and s. R is the x-coordinate of this random point r here, and s is the value calculated using this formula. For a 256-bit curve, r and s will be a 32-byte value each, so an ECDSA signature will be 64 bytes in total. There are two formats in which these signature values are stored in practice. The simplest form is to store it as a 64-byte value, where the 32-byte r and s are concatenated together. The other format is using ASN1 derencoding, where these two values are encoded as ASN1 integers into an ASN1 sequence. When assigning data with ECDSA, the digest infrastructure is not used, but a raw hash value of the data to be signed. This means that the verifier has to know what hash function was used to create the signature. Now, what is the largest value we can sign using ECDSA? This depends on the curve, or more specifically on the order of the curve. The requirement is that the bit length of the hash value must not exceed the bit length of the curve's order n. So this means that it is useful to sign a hash value produced using a hash function whose output length is of the same length as the curve. So for a 256-bit curve, use SHA-256. It is possible to sign a hash of any length, but longer hash values must be truncated to the bit length of n most significant bits. For instance, if we would have to sign a SHA-512 hash, then effectively only half of it would be signed, thereby providing the same security level as provided by SHA-256 hash, right? Shorter hash values must be left padded with zeros. This will not change the integer value of the hash, but such a padding may be needed if an ECDSA library expects hash value to be the same byte length as the size of the curve. Another thing we should note is that this ECDSA algorithm is probabilistic, meaning that the signing of the same data each time will produce a different signature value, because each time a different random nonce k is used to generate a signature. And this is an extremely important requirement for the security of the scheme, that this nonce key must be secret and random. Because if we can somehow learn the nonce key, then we can recover the private key from this value s. This is how we can do it. So if we know key, we can multiply s with k to get rid of this k inverse, because k times k minus 1 equals 1. Then, since the hash is known, we can subtract the value h from this value, then multiply this value with R inverse to get rid of R, and that's it. We have obtained the private key value D. Basically, the secrecy of this nonce K has to be protected in the signing process the same way as the secrecy of the private key D. Furthermore, it is not enough for this nonce to be secret. It must be unique for each signature, because if we have two different messages signed using the same nonce key, we can recover the nonce key and then the private key. Even more, if there is only some slight bias in some of the bits of the nonce, then by collecting many signatures and using lattice-based attacks, it is possible to recover the private key even if we don't know what exactly that bias is. Quite scary. So this requirement to have access to high-quality randomness when creating each signature is a significant drawback compared to RSA. In RSA, good randomness is needed only in the key generation process. But here we need good randomness for every signature created. Otherwise, we risk leaking the private key. And there have been several high-profile cases where imperfect ECDSA implementations have been used to recover the private keys. A solution to avoid this risk is to use the deterministic ECDSA, where the nonce key is generated deterministically by deriving it using an HMAC from the hash and the private key values. The method is described in this RFC. Alright, but let's take a look at how to verify this signature. For verification, we need the hash of the data, signature values R and S, and the elliptic-curve public key point Q. First, we have to calculate point R prime by multiplying generator G with this value here and adding the resulting point to another point, which is obtained by multiplying public key point Q with this value here. The S-1 here is the modular inverse of S modulo n, calculated the same way as here for K inverse. Verification is successful if the x-coordinate of this point here matches the signature value R. So why should this verification work? By simplifying this equation, we can indeed see that the x-coordinate of this point will be equal to R, because this equation is equal to K times generator G. Here is how we can rewrite this equation. First, we can replace this public key Q with D times G, because this point Q was obtained by multiplying the generator G D number of times. So we replaced Q with D times G. Then we see that here and here we have a common term G, which we can move out from the equation. So we moved it out, and this is what is left inside the parentheses. So this value inside the parentheses should be equal to the nonce key, right? Next, we can open these parentheses, and this is what we will obtain. Here, we have a common term S-1, which we can move outside the parentheses. Here we have moved it outside. Now we can replace S with this equation here. And this is what we get. Now we can open the parentheses, which means that this inverse will go here and here, like this. We know that a value multiplied with its inverse is equal to 1, so we can replace this with 1. And we are left with this. And we know that the inverse of an inverse is the value itself. So as a result, we get that R prime is K times G, the same as here. and it must hold that the x-coordinate of this point is equal to r, in case the signature is correct. Okay? So in the verification, there are 2 point multiplications and 1 point addition. So performance-wise, verification is a bit more expensive compared to signing. An important difference compared to RSA is that it is not possible to recover the value that was signed from the ECDSA signature. So in RSA, we could take a signature value, decrypt it using the public key, and see the raw bytes that were signed. In ECDSA, that is not possible. Therefore, signature verification failures are harder to debug. Now, there are a couple of corner cases in signing and a verification process that I did not mention, but you have to check and handle. The first is to validate the public key point Q in the verification process. This will also ensure that a public key point has not been corrupted and has been correctly decoded. Then you should verify that the signature values R and S are in range 1 to n-1. This is not exploitable for NIST P256 curve, but may be exploitable for other curves if this verification check is not implemented. And finally, in signing process, it must be checked that the calculated value S is not 0. If it is, then the signing process should be restarted by picking another random nonce key. The probability of S being equal to 0 is negligible, but still, such check should be implemented. The homework task is to create an ECDSA utility. Implement an ECDSA signing and verification utility, ECDSA.py, that works in sign and verify modes. In the signing mode, it reads the private key, the file to sign, and produces a signature. This signature file contains a Darren-coded structure encoding the R and S components as integers. Use NIST P256 curve, also known by this name, and SHA-384 to calculate the hash of the file to be signed. Now, for a 256-bit curve, it would be more optimal to use SHA-256 here. But here we are using SHA-384 to check that the hash value is correctly truncated to match the size of the curve. You have to implement the ECDSA algorithm using yourself by performing EC point operations. I will show you how to do it in a slide. And just a note, the modular inverse x mod n can be calculated using the PO function. As a test case, we generate an elliptic curve key pair and export the public key. To test signing, we create a file that contains 1 megabyte of random data, sign it using our utility, and verify the signature using the OpenSSL digest utility. To test verification of the signature, we create a signature using OpenSSL, verify it using our utility, and it should output verified OK. To test a failed verification, we create a signature using a wrong hash algorithm, so this will sign a wrong hash value, verify it using our utility, and it should output verification failure. To perform raw elliptic curve point operations in Python, we use this small module that is available in the course repository. Here is how to use it. The generator is available by accessing this G attribute. It returns an EC point, which is a Python list containing the X and Y value of the point. We can access X and Y values using the list index here. Then we can use the mul method to perform point multiplication. The first argument is the point and the second is the scalar. And this method will return the resulting point. Be aware that the multiplication here is vulnerable to side channel attacks. So for production code, you should use a decent cryptographic library to perform EC operations when the private key is involved. The order of the curve is accessible using the n attribute. If we multiply any point with the order of the curve, we get to the point at infinity. the point at infinity is represented as a list containing two non-values. Multiplying a point by n plus 1 provides the same result as if we multiplied it by 5. So you see, the elliptic curve group is cyclic. If we were to add a point to itself n times, we would return to the initial point. To add 2 points together, we can use the add method. If the points are the same, it will internally call the double method, so there is no need to call the double method directly. Adding a point to itself is the same as multiplying the point by 2, as you see here. We can use the valid method to check if the point is on the curve. For example, this point is not on the curve. Then we can compress a point and decompress, but the point compression will not be necessary in the homework. Since you will have to generate a random nonce in a specific range, let's look at how to generate a random number in a given range. So let's say that we have to generate a random integer in range 0 to 200, but our random number generator is only able to give us random bytes. So what can we do to get a random integer in range from 0 to 200? The first idea is that we can get one random byte and convert it to integer. However, the problem is that one byte can contain values from 0 to 255, so if the returned byte value is larger than 200, we are in trouble. A simple fix would be to reduce the value modulo 201. This would guarantee that the result will never be larger than 200. It would indeed work, but the problem is that the result will not be a random value in range 0 to 200. So if you look at the probability distribution of values generated by this code, we can see that the distribution is not uniform. We see that the values from 0 to 54 will be twice more represented than the values from 55 to 200. The reason is because the byte values larger than 200 will not be discarded, but will be reduced by 201, thereby doubling the probability of the values 0 to 54 occurring in the result. So while the probability to observe these values will be 1 out of 256, the probability to observe these values will be 2 out of 256. As you see, this is a significant bias that may lead to a compromise of a crypto system. One idea how to decrease the bias is to take a larger random value. For example, instead of using a 1 byte value, we can use a 64 byte value. This way, some bias will still be present, but it will be so negligible that it will not be distinguishable in practice. While this hack may work in practice, we should instead use a method that will provide us a completely unbiased distribution. So, to generate unbiased numbers in a specific range, the rejection sampling method must be used, where we regenerate the value until it is in the required range. In this example, it means that we would throw away byte values that are larger than 200 until we get one that is in the expected range. So you should use this approach when implementing the ECDSA nonce generation in the homework. Alright, here are some questions and good luck with the homework.